Hello again. Today I want to look at planet promotion. This is quite a nice little aspect of geometry that looks not very well appreciated. Now, the fact of the matter is that planetary motion is enormously complicated, and you may well have heard of something called the three-body problem. Indeed, once we get lots of planets involved, then the situation really does become quite complicated. So I'm going to follow what a lot of physicists do and sort of reduce the situation. But we have to remember that when we reduce a situation, we've got to remember that it is a reduction and not the bigger picture. So what about the simplest case? Um, you've probably heard that Newton's law of gravity. Newton says. So basically, I've got sun and planet, and the distance between them is r. We know that Newton says that the force is given by uh, the universal gravitational constant times the mass of the sun. Okay, the sun has mass m, planet little p is little m over r squared. And so what we're going to do is we're going to look at this little situation and try and understand what's going on. Um, the first thing I want to do is not to look at specific situation at all, but to look at something of which this is a particular case. We're looking at what's called central forces, directed to a fixed point. So basically, if I've got a force, it's the force is everywhere directed to a point. Um, and further, and depends only on the distance to that point. So essentially, the force on the system is a function of the distance from the point, from the central point to any other point. That's that's the situation. Now, because if you have that, then you have symmetry. You have spherical symmetry, which means that we can rotate the system and not change it, which is really quite wonderful. We have a symmetry. So if in this case we can sort of rotate the system out, we don't doesn't matter. If we can do that, then what we have got is a lovely little theorem by a female mathematician, um, remarkable lady. I've got to spell her name right. Of Emmy Noether. She has a theorem. Emmy Noether's theorem says there is a symmetry. There is a conserved quantity what does that mean? Well, it means that some aspect of the motion under a central force that is constant. And in this sort of case, when you've got a rotational symmetry, we have angular momentum. Now, angular momentum is a vector, i.e., it's got direction as well. It's not just a scalar quantity. And if a vector is conserved, that means its direction is conserved. And if its direction is conserved, then it means that the motion of a planet is contained in a plane. That means it doesn't go whizzing about in all three dimensions. It's stuck in a plane. And if you look at a lot of astronomical objects, think of the solar system. All the planets do lie more or less in a plane. Uh, the dwarf planet Pluto is a bit of an exception because its plane of rotation of orbit is slightly skewed to the rest of the planets, but nonetheless it still stays very much plane on the whole. Um, if you look at it, from a wider, but more complicated uh, viewpoint, it does get more complicated. So everything's contained in a plane, and that actually makes things simpler for us because we can now start doing a coordinate system. So here is my sun. Here, here is my planet P. The distance between them is r, and it means that I can just put an arbitrary place, an arbitrary line, and call that theta. Now, already, as I say, we've got angular momentum is conserved. Angular momentum is directed perpendicular to the plane, so we don't have to worry about it. But it has magnitude. I'm going to call it mu, but it's constant and it's given by r squared theta dot. And that's actually really quite fascinating. Already we have one of Kepler's laws here, because if I try and consider the area the planet sort of sweeps out, I'm going to draw it like that because it's all wiggly. If I look at that area, and I have the other way being theta, uh, and this is at time t, and that's theta equals 0 at time t equals 0. And if that's the area, then the area swept out by theta is, according to the rules of geometry, the area is going to be this. Okay, I'm slightly abusing the notation here, but I hope you can see what it means. But hang on a minute, you see the thing is I can now regard that as integral from 0 to t of r squared times d theta by dt. And remember that theta dot, there we are, that is mu. So this is the integral from 0 to t of mu dt, which is a nice integral. Sorry, there's a half in there, technically. Put the half in over 2. As it says that you get mu t over 2. And so we've got Kepler's second law already. at equal areas are swept out. Okay, so let's just it's all nice and oops. That's a nice thing to have. Kepler says equal areas swept out equal times. And that's quite nice. That enables us, and we'll see that perhaps in a later talk, perhaps next talk, I might actually look at the relationship that actually gives us with the time a planet takes to orbit, related with its distance from the sun. So now, what I now want to do is I've got a conserved quantity. So we've got a conserved quantity, and that is that r squared theta dot is equal to mu is constant. And of course, in another Newtonian system, there is another constant of a constant, and that would be a constant of energy. So the energy is kinetic energy plus potential. And in this system, the kinetic energy is given by m times, so m over 2 times the square of the square of the speed, so the magnitude of the velocity, the square of the speed, so that's given by that. So you can see the radial component and the tangential component there. And the potential energy, now the potential energy in a gravitational system, we measure in a way so that it increases to zero. It sounds a little counterintuitive, but it means that when you're at infinity, there's no potential of you moving towards the center. It decreases as you get further and further away. And because it's decreasing, so it's easier, so it's going to be a minus sign. And then you've got the famous, this is the gravitational potential, GMM over R. So you can see how that's related with the famous inverse square law. So if I just do a couple of bits and pieces with this. So first of all, what I'm going to do is I'm just going to simplify this a little bit because what we're going to be interested in is really the behavior of the planet. So multiplying out. So basically what I've done is I've got rid of the stuff in front of the derivatives. So we've got that, and we've got r squared theta dot equals mu, which means that theta dot is equal to mu over r squared. And so here what we have are our, it is essentially our equations of motion. For a simple planet. I'm also simplifying a little bit more as well because really two planetary bodies orbit about the center of mass between the two. So I'm simplifying it a little bit further and sort of trying to um, not worry about the business of center of mass, particularly if M is significantly larger. But there is that little thing. Now, we're interested in the shape. That means we're interested in R in terms of theta rather than r in terms of t. We're interested in the shape of the orbit. So what I'm going to do is I'm going to try and turn everything into derivatives in theta rather than in terms of time, which is going to make things a little bit easier. So it's r dot. So what do we mean by r dot? Well, remember that's the derivative with respect to time. And I use a chain rule. Here's its chain rule. And we know what d theta by dt is because that is theta dot. That's this thing. So now I've got everything in terms essentially of what I want. I've got an equation of motion that's going to give me the shape of the curve rather than the what's happening when. So now let's just plug that in and see what happens. So I've got 2e over m. Yeah, there's going to be quite a few little constants flying about. We'll try and simplify those a little bit later. But let's not worry too much. So there is the derivative. There's r dot, which now turn into terms of theta, plus r squared. Now here is theta dot squared. I've got the potential energy over here. So that's for kinetic energy, or in terms of or in terms of theta. So let's just simplify that out a little bit too. And we notice that r mu squared over r to the 4 dr d theta squared plus mu squared over r squared minus g 2gm of r. Now you notice you think, so how on earth, if I try and solve that differential equation, how on earth am I going to do it? The first thing we notice is that it'd be easier not to work with all those 1 over r's. So what I do is I'm put, let's simplify it out. So instead of having 1 over r, let's look at 1 over u. Let's try and get rid of it by putting r equals 1 over u. Because if r is 1 over u, then u is 1 over r, and everything sort of turns into nice into u's. So that means that dr by d theta is equal to minus 1 over u squared du by d theta. Let's just plug that in, see what happens. I've got 2e over m, so that's the energy factor. Okay, here we go. So what I've got mu squared r to the 4, 1 over r to the 4 is u to the 4, dr d theta, d half the theta, we'll need to deal with that, which is minus 1 over u squared du by d theta squared plus mu squared u squared minus 2 gmu. Already things are starting to go really nicely because look, what have I got? In that first term there, I've got, first of all, the minus sign evaporates with squaring. Secondly, we've got a u to the 4, divided by u to the 4. So that goes away. So I've now got du d theta squared plus mu squared u squared minus 2gmu. And so we might as well divide by mu squared. That's going to make everything look a little bit more complicated at the moment. But you'll see we're going to try and be a bit judicious. Right, now what I'll do is look at this bit here. Because that looks rather it looks rather interesting. It sort of looks like a square, but not quite. So what I'm going to do is I'm going to say, right, well, I've got this. We've got a 2 something there, 2 times something there times u. Right, so what am I going to do? I think what I'm going to have to start doing is I'm going to have to start putting in some new, uh, let's try and simplify things out so it looks transparent. So A is 2e over m mu squared. So that's the left-hand side. So just leave it as A for the moment. And B, we're just going to put as, well, we're going to be having stuff on that thing that's being halved there. Because I think what we would like to do, it would be nice if we could complete the square. So I'm going to do that. And then what have I got? Because I've got A equal du by d theta squared plus u squared minus 2bu. And now what do you do? Well, you think so far, that'd be nice, because what I can do is now just add in the b squared, that, plus u squared minus 2bu plus b squared, and all of a sudden something nice happens, because you see that gives us, so, well, what we do now, so we now know that du by d theta squared is equal to a plus b squared minus u minus b squared. What I'm now going to do might be counterintuitive, but I want you to see something. Now, this bit here, 1 minus something squared. Wouldn't it be nice? Wouldn't it be nice if that were a trig function? Maybe they'll have to do a little bit of work. But it would be really nice if we said that I had a trig function. So say something like cos phi equals u minus b over the square root of a plus b squared. Well, can I do it? Can I do a plus the square root of a plus b squared? Because we know technically e could be negative. But that thing would only really be negative if we had no kinetic energy at all to begin with. So we're going to assume that's positive, to be honest. So let's just assume that a plus b squared is bigger than 1. So assume that. If we do that, well then let's just look at so put the derivative. The derivative of that. So that gives me chain rule there gives me minus sine phi times d phi by d theta equals over here I've got 1 over a root a plus b squared times du by d theta. Okay, so what have I now got? I've now got du by d theta is equal to root a plus b squared minus times sine theta times d phi by d theta. And then what we're trying to do, we're trying to look at this thing here. We now have the du by d theta, so that's squared. That's du by d theta squared equals a plus b squared times 1 minus, well, isn't that? That is what we wanted. This thing here is what we wanted to be called cos theta. So we've got cos squared theta here. Sorry, cos squared phi. Right, and so now simplify it out. Minus sign goes away. A plus b squared squared sine squared phi d phi by d theta squared is equal to, now you see things start to do, right, that's it, 1 minus cos squared is sine squared. How convenient. So now what happens, look at this beautiful thing, because you see that and that, and we are left with d phi by d theta squared equals 1, which means that that phi is plus or minus theta plus a constant. Now, you're just going to remember the system is rotationally symmetric, right? So which means that I can just rotate it in such a way that phi is simply theta. And a good choice of coordinate system. So if you've got the wrong coordinate system, just rotate it until you've got the right one. It doesn't matter because it's a symmetric. It's a symmetric system. It's a rotationally symmetric system. So now what have we got? We've now got phi equals theta. Right, now we've got the lovely job of going backwards and plugging everything back in. So we know that a lot of the work we've really dealt with, because we now know that phi is equal to theta. That means that actually what we'll do is, as soon as I have the power, which is rather lovely, copy that. No? Oh, oh, never mind. Oh, never, my friend. Cos theta is equal to u minus b over root a plus b squared, which means that u is equal to b plus a plus b squared times cos theta. And u is 1 over r, so r is equal to 1 over this, 1 over b plus a plus b squared cos theta. One more bit of simplification. Take out that b. What happens if I do that? Well, I get this. Now, this quantity here becomes quite important because, well, cos theta has maximum value 1 and minimum value -1. So the minimum value, what do we know? We know that 1 plus root a plus over b squared plus 1. Well, that is going to be less than, when oh, we've got to get it. It's going to be less than 1 plus a, because cos theta has a maximum of 1, so it's less than that, but it's also bigger than, also bigger than 1 minus this root of a. Okay, so the denominator here is sort of sandwiched between these values. Now, the thing is, This thing here is very that be zero, depending on A and B. And if that's zero, then we have some infinities. Then the rate, the distance between the planet and the sun becomes infinite. But for certain values, it's not. And this is one wonderful thing. So we know that if we have A over B squared plus 1, if we know that's less than 1, and remember that the square root sign there is positive, then if it's less than 1, then there are no R equal infinities. And in that case, you've got a bounded curve. And if you would you put this on the computer, this is the orbit becomes an ellipse. This is what we're used to. And that's what Kepler observes. That's Kepler's first law that planets travel in ellipses. If over b squared plus 1 equals 0, so equals 1, then we get 1 r equals infinity. And that would mean the orbit is a parabola. And that's actually quite a rare system, thinking about it, because it had very precise values. There was only one that the b squared would have to be actually equal to, um, a would have to be equal to 0 for that to happen, which is, if you remember that a is related to the total energy in the system. If the total energy in the system is actually 0, then that's where you'd be. You'd end up with that, and you'd end up with a parabola. But finally, if you've got negative energy in the system, which would happen under certain circumstances, remember the negativity of the energy results essentially from the way we've measured potential energy. So if it's bigger than 1, we have 2 r equals infinities, which would mean the orbit is a hyperbola. That we see, I think, very much in comets and bodies from the depths of the solar system, from places like the Oort cloud. That would be the situation for our planetary motion. So it all depends on the relationship. Remember, A was related to the kinetic energy, B is related to A is equal to the total energy in the system, and B is the related to the potential energy in the system. And as a result, what you have is you have this wonderful interplay. So if you've not got enough energy, if you've not got enough potential energy in a system, so if you're not got enough total energy in the system, then you don't have the planet doesn't escape the sun, so it orbits. But if you've got enough kinetic energy, if you've got enough to give it a boost, then you can escape the system and you will go out in a hyperbolic orbit. And that's what a lot of astronomers like to use when they do gravitational slingshots and these sort of things, which is quite wonderful. The problem we've not looked at is the question of Kepler's third law, which relates the period of planetary orbit to its average distance in the sun. I think I would like to do that at a different time. That will probably not be a long video, but I think you've suffered long enough. Anyway, have a great day. Look after yourselves. Hope all goes well. Bye bye.